Thanks for the invitation. It's a pleasure to be back in Stockholm and at KTH. The weather is beautiful, and I noticed that the nights are very short now and lots of sunshine. It's great to be here. So the title on the screen is slightly modified, but only slightly from the title that was in the advertisement. I didn't mention Morse functions here in the title, but I will say just a little bit about what the role of Morse functions or Morse fields is. So the talk I will promote as a text. This is the March issue of the Proceedings of the IEEE, and the issue is dedicated to the interface of humans and smart machines. And as I was telling Xiaoming before the lecture, there's a lot of interest, I think, throughout the world, but in the US funding agencies in particular, in trying to understand a little bit more about how you can make human and machine operation together more effective in light of the fact that machines are becoming increasingly intelligent. And there's a number of different ways that you can approach this. And this particular talk is going to be focused on the notion of information acquisition. So suppose you have some robots, mobile robots, they're sensor enabled, and you want to acquire information. You want to have these robots function as part of a team of, that involves humans as well. The question is, how do you program them so that they are most effective participants in this team that's going to go out and acquire information? And you can think about these questions in lots and lots of different contexts, but the context that I want to think about it in is, suppose that there is a scalar field that represents some quantity of interest, and it may be something like CO2 concentration in the atmosphere or the level of intensity of a substance in the environment, maybe a toxic substance, and you want to have little sensor-enabled robots go out and explore the domain and try to acquire information as rapidly as possible about the nature of what's going on in the environment. And one of the key things in what I'm saying is that it's always wants to be acquiring information as rapidly as possible, and I'll come back to that point. So this is, I like this guy's face. This is Robert Adler. Robert Adler has explored the interface between differential geometry, differential topology on the one hand, and random processes on the other, and has developed a sort of a body of theory that has to do with what's the geometric nature of random fields that have certain correlation characteristics, and ask questions such as, when might these fields be Morse fields, which implies a certain level of differentiability. So that understanding randomness in this domain is a bit different from the randomness that engineers frequently think about, which is the randomness of white noise processes, where there's no correlation at all from point to point. Whoops, go the wrong way. So this is a rough outline of what I want to talk about. The relationship between topology and information. Talk a little bit about the information theory of functions. I will mention motion primitives for robotic reconnaissance. That is to say, what are the types of feedback control laws that might be useful in making robots autonomously explore certain aspects of a random environment. I'm going to talk about information in the specific context of reconnaissance, I'll talk about the topology of unknown fields, and I will conclude, if there's time, telling you about some experiments that we've done in the lab with humans guiding robotic exploration and what we have learned about human biases in terms of the kinds of features that they look for and the efficiency that they go about looking for these in exploring unknown fields. So just by way of information, a quote from Shannon and Shannon's brilliant 1948 papers that appeared in the Bell System Journal. This will serve as the setting for the kinds of information metrics that we want to talk about, the kinds of information metrics that were proposed originally by Claude Shannon. So what we're interested in is understanding the kinds of decision-making that are useful in guiding reconnaissance and exploration. We want to understand a little bit about the cognitive psychology of spatial knowledge. Other things are understanding what people perceive to be interesting in visual images. And finally, we'll talk a little bit about data compression and sensor fusion for continuous data. So this is just a quote from the psychology literature about the ways that people have been, psychologists have been thinking about knowledge representation as it applies to the way people actually think and about how people remember spatial information, how they store it in their own minds, and how they use it. And this has sort of been a theme that has emerged at the interface between cognitive psychology and computer science. So here's the kind of real problem that has motivated what we want to think about. Let's see if these are going to play. Maybe not. But what you would have seen in those previous pictures, let me go back, had they played, is a movie rendering of the oil spill that was in the Gulf of Mexico in the US a couple of years ago. I think that probably made enough news worldwide that people in Sweden were well aware of the issue. And one of the things that was of interest at that time was to track the progress of the pollutant. And so the idea of sending out robotic search vehicles like the little submersible vehicle that you see there, it's called a Slocum glider, which is designed for robotic operation in the ocean for long periods of time, a matter of multiple weeks, and to keep track of the boundaries of the pollutant and to keep track of not only the boundaries but how the concentrations might vary spatially. Okay, so the kinds of decisions that are involved in exploration are exploration versus exploitation decisions. Remember, this is for rapid information acquisition that we're interested in. And if you are exploring an unknown domain and you want to do this as rapidly as possible to acquire information about something that's unknown, then you typically have to make a choice at every instant, which is, if I'm finding something that is of interest, should I stay where I am and look around the immediate vicinity to see if there are other things that are of interest? And if I'm doing that, that's called exploitation. I'm exploiting a known region of interest that I've identified as being of interest. The choice is instead of doing that, I may want to go off and explore somewhere else and try to find another region of interest. And so the question is, when have I sort of exhausted all the possibilities in one region and it's time to go on to the next region? And making that decision in sort of the time-optimal way so that there's a good balance between speed and accuracy, or speed and information acquisition, is a tough decision. And people tend to make these decisions intuitively, and the question is, can you sort of put some metrics on this and understand, where in real time the optimal breakpoints are between depth versus breadth. So how do we think about whether information, spatial information, is interesting or not? And this is where connections with the classical thinking that has matured from Shannon's ideas and the ideas of others, to be fair, comes up. So what I want to do is I want to think of functions, a function mapping a domain X to a range Y as being information channels. And the way I think about this is that f, the function, provides information in the range about the domain. And one of the things that I might think about is driving along a road. And my claim is that the road is going to be interesting or not depending on how much the curvature is changing. So infinitely straight, long roads, as you get in the West and the Midwest of the United States, I claim are not at all interesting. And circular tracks, as you get in certain types of automobile racing, are not at all interesting. But courses that you might drive along that are constantly changing their curvature are in fact interesting, and they require a lot of attention on the part of the driver. So if curvature is a function, then the variability in this curvature is going to be a measure of how interesting the road is. So keep this idea of variability and the amount of interest that an object holds as being key. So we can apply this in a spatial domain, okay? And spatial, a function or a field, a scalar field defined on a spatial domain is going to have peaks and valleys, and there's a cartoon rendering on the left there. And the ways that these peaks and valleys, the geometry occurs, and the height of the peaks and the numbers of mountain ridges between the peaks is an indication of whether or not these things are going to be of interest. And so if you think about, for instance, looking at a plot of ground that may be a kilometer on a side, and you want to know whether or not there are animals or humans concentrated in a certain region, then one of the ways that you can detect, there's many signatures of life forms. There's thermal signatures. CO2 is actually something that's easy to measure and is a good indicator of whether or not there are breathing creatures in a given area. And so you can measure these things. And if you see a bunch of peaks concentrated in a certain part of this square kilometer plot of land, then you decide that that's of interest. So one of the things we're going to think about is taking this variable field, and we're going to plot level sets or contours, and because these are things that we can extract as information. And what you can do is you can think about a mobile robot going around and mapping level contours. And when I talk about feedback control laws that aid in information acquisition, the type of feedback control law that would track a level set based on sensor readings is the kind of feedback control law that is of interest. Okay, so here's how I'm going to think about the information content then of a scalar field. I've got my field, and it's got a certain range from a low of A to a high of B. This is a real interval. And typically, every sensor, no matter what it's sensing, is going to come with a range, sort of a manufacturer's suggested range of interest. So we'll take that as being associated with the problem. And then what I'm going to do is I'm going to form a domain partition. And the domain partition is going to be the set of connected components that correspond to these little subintervals in the range partition. So these are going to be these level sets, but in particular the regions between the level sets. So they're going to be annular regions, typically, topologically equivalent to annuli. And what I call the data-induced partition then gives rise to a metric which looks a lot like Shannon's entropy. Okay. And so thinking of this metric, then I'm going to make information acquisition be my search metric, the metric that determines for me which way to go in the decision of exploitation versus exploration. Should I continue to map a certain region and find more nearby level contours, or should I go off and explore someplace else? And my criterion, very simply, is going to be, with every mapping of a contour line, how does this information metric change? If it changes a lot, then I'm concluding that I'm gathering useful information, and I continue to map more contour lines. If it doesn't change very much, I'm going to go look somewhere else. So this gives me the idea then of taking these partitions of the domain and making a partial ordering on them, and that partial ordering is going to be determined by the information content that is associated with each. And what you can do is you can think about sort of monotone structures, standard fields that just have one peak, cones and spheres, but Gaussian mountain ranges as well. And you can associate these information metrics to each one of them. And one of the things that's important to point out is that single peaks have limited entropy. And the entropy that they have is bounded above by log n, where n is the number of cells in the partition of the range. All right? And you can never get above that if it's just a single peak. And the information is concentrated in different regions depending on the shape of the peak. All right? So that if you take some canonical surfaces of revolution just to, for the sake of study, then what you find is that as you map contours, the information that you acquire grows at different rates. And in figure 1, up in the upper left-hand corner, you're acquiring information at basically a linear rate. In figure 2, at the beginning, you're acquiring information at a superlinear rate, but it really tapers off. It tapers off much more in figure 3, and then in figure 4, there's a very slow rise, followed by a high rise, followed by a tapering off. So I don't want to dwell too much on these things, because single peaks are, in terms of this metric, are not the most interesting ones to study. But there is this bound on that if you have n cells in your domain partition, that the information content is never going to be more than log n in terms of this measure. Non-monotone functions, however, have lots and lots of more interesting possibilities. And so if you have a number of peaks, then the information content is going to be higher. Okay, so let me talk a little bit about partition entropies. Partition entropies are interesting, and I think they pretty much grew out of the Russian school around Kolmogorov, studying these things as an alternative way to think about information theory, and this was quite some time ago. So the idea is that if you have a domain and you have a partition of the domain, which we'll call alpha, then there is an entropy associated with it, and it's given here, and the interpretation here of the measure of a cell in this partition is roughly like the measure of doing an experiment to find something that's located in the domain somewhere, and the measure of a cell in the partition is roughly the probability that you're going to find it within that cell. And just like all of information theory, you can define notions such as conditional entropy. And I won't go through the formula in detail, but if you've read Gallagher's book or the late Tom Cover's book, you know that these are familiar constructions. And once you make these definitions, then you can write down a bunch of inequalities that the conditional entropy, for instance, of one partition conditioned on another partition is always less than or equal to the unconditional entropy of the partition that you started with. And in particular, the conditional entropy of a partition alpha conditioned on a partition beta is 0, if and only if beta is a refinement of alpha. Okay, there are other partial orderings. I won't read through all of the bullets on this list, but if there's time or as these things come up in the course of the lecture, we'll refer to these inequalities. And these are very standard information theoretic types of inequalities. All right, so let me talk a little bit about level crossings, excursion sets, and the height map of random fields. And this is the connection, where the connection comes in between differential topology and the information theory of functions. So just excursion sets, I'm not sure who coined this term, but it's used very much in these books that I mentioned at the beginning by Adler. These are the sort of the differentiable field version of first passage sets or level crossings in normal stochastic processes. So if you think about there being sort of a level of the field that you want to study, you can study the set of elements in the domain where the value of the field exceeds the prescribed level. So this is illustrated here in this figure. So think of passing a plane through the graph of the field, and the intersection of the plane with the field is going to give you some sets. And in this case, we have a disconnected set of two curves, one of which looks like a peanut and the other which looks like a circle. So as you make more and more of these level curves, set of level curves, you get a graph that might look something like this. And of course, one of the things you're interested in when you, if you want to think about identifying important characteristics of a differentiable field is you want to know where the critical points are and where the critical level sets are. All right, and so this is a cartoon rendering of critical points and critical level sets for index 0 critical points. These are the relative maxes, index 1 critical points, and index 2 critical points. All right, so a critical level set of F on a compact domain is a connected component of values in this set of connected components of level sets that corresponds to the critical point. And one of the things that we're going to assume here is that we're dealing with a generic Morse function, which means two things. It means, one, that the critical points are all isolated points. And it means, two, that the critical values are all different, so that we don't have the case where we have two relative maxes, say, that have exactly the same value. Okay, so denoting the critical level sets, the set of critical level sets, as I have in this slide, then I'm going to introduce a particular partition of the domain, and that's what I call the topology-induced partition, and it's a very simple object. It's just the domain itself with the critical level sets removed. All right, so that means that there's a puncture in the domain everywhere there's a relative min or a relative max, and there is a one-dimensional curve that is topologically equivalent to a figure 8 that's removed for every index 1 critical point. And that's all there are. And that follows from the assumption of the field being Morse and the assumption that it's not only Morse, but it's a generic Morse function. So that's in 2 dimensions. You can do this in higher dimensions, in which case the critical level sets are similar in terms of their own dimensions, but of course the dimensions will differ, and this is just a cartoon rendering of a particular function and a particular element in the topology-induced partition, which is now, it's whatever the cells in the partition, of course, have the dimension of the ambient space or the domain itself. So this is a case where the critical, the elements in the topology-induced partition have dimension 3. All right, so this is just going back to the case of planar domains. And in this case, the critical level sets look like this. There are points that correspond to maxes and mins, and then there are these figure 8 type figures, which are, I call topological characteristic motifs. And these things can get complicated, of course, depending on the nature of the field. But we're assuming a certain amount of smoothness so that the field is a Morse field. And so that means that as they get complicated, they can't get too wildly complicated. So associated with this type of topological motif, we're going to associate a graph, okay? And the nodes in the graph, the vertices, correspond to the critical level sets, and the edges correspond to the cells in the topology-induced partition that connect the critical level sets. And it would be a subject for a second talk, but you can write down control laws, and we have a little library of these things that we use in the lab, actually. They work, and you can have little robots go out and map domains. And the 2 motion primitives that are of interest are level set following and gradient following, gradient contour following. So for this field, we can basically map contour lines, and then we can map ascending and descending gradient lines. And so I'm going to introduce a second partition now, and that's the data-induced partition. And the data-induced partition is what the robot would find if it went out and started mapping contour lines. So it sends back the values, the contours, the point locus of the contours that it maps, And then all of the, from that you can infer, what the cells between the contour lines look like. And those cells between the contour lines constitute the data-induced partition. All right, and so here's an actual photograph of a little robot that we used to use in the lab. It's got a mote on it, which is a little wireless sensor. So this is a dynamic sensor network. And we're going to have this little guy go out and map level sets in some unknown domain. And here you go. There's the little robot, and you see it's sending back radio signals. And so I get the contour rendering on the screen here. And as soon as it maps a contour line, it goes off and maps another domain. And these little features you see here in the video, those are just magnets that you buy at the hardware store. So we create our domain to be explored in that realm. Okay, so now we go back to the definitions and the conditional entropy. So the sets M here, M sub I belongs to script M. These are cells in the topology-induced partition. And the V's, which are in this script V, are cells in the data-induced partition. And what I want to compute is the topology-induced partition conditioned on the data-induced partition. And if I will have found a data-induced partition at some point that contains all of the information that is in the topology-induced partition, then this conditional entropy is going to be 0. So that's going to be my search criterion, that I want to drive that conditional entropy to 0. And so the theorem is that, and this just follows from general considerations, that this conditional entropy of the topology-induced partition conditioned on the data-induced partition is bounded between 0 and the entropy of the topology-induced partition. And it's 0 if and only if the data-induced partition is a refinement. All right, and so this theorem gives a very nice result about the ways in which these two partitions are related. And so I'm going to define this quantity delta sub j to be the relative height that if I have one of these annular regions in the partition, in the topology-induced partition, the relative height that it spans in the range of the function. So it's the sup over all set points in the set M sub j minus the inf compared with the same difference over the entire range of the set, the domain that we're exploring. And making this definition, then I have this interesting inequality here that the entropy, the partition entropy corresponding to the field F and the data-induced partition minus the log of n, which is the number of cells in the range of the partition of the range, is always less than or equal to the entropy of the topology-induced partition plus this factor here, which weights how much variability there is on a particular cell in the topology-induced partition against the relative size of that cell. The quantity on the left, there's a few things that are of interest about this. First of all, this limit is finite. So if you read some of the classical books on partition entropies. And these are really wonderful if you like very elegant, clean, pure mathematics. They led to something called that was the definition of topological entropy of mappings. And people in the control and systems theory world have thought a lot about how topological entropy might actually play a role in the kinds of information-based control that was popular about 5 to 10 years ago that involved the data rate theorem. And this concept of topological entropy, which is basically a concept of what the variability of a nonlinear function is and how much information is needed to capture the way that the function, if you, given that it maps a scalar domain into a scalar domain, given the amount of information that could be lost due to the fact that the function is everywhere expanding points under iteration. And so this is an idea that's come up in this particular context. And if you're familiar with information-based control and the data rate theorem, you may be aware of some of this work. Anyway, this is kind of a higher dimensional version of topological entropy here. But it's really exactly the same kind of idea. And the fact that this is always going to be a finite limit, that is to say that the entropy doesn't grow that much faster than log n, is of interest, as well as this particular bound on the rate at which this grows. So there are a number of interpretations of this, that the critical sets of an unknown field, for one thing, contain all of the information that you might get by exploring using one of these sensor-enabled robots. All right? So there's another set of questions that are of interest. This is all well and good that the topology somehow encodes all of the information you might ever extract and upper bounds it. Do humans take this into account if they're exploring an unknown domain? So that was a question we got interested in. And then the other question is, having said this, what does it imply for the design of algorithms for reconnaissance and exploration? So the goal then is to design algorithms for sequentially refining the topology in order to climb information gradients aimed at learning the entire topological structure. And the caricature of the algorithm that you might want to develop is to initialize a partition, a data-induced partition, to start out to be just the entire domain itself. So it's a single element that's in this set, script V. And then the conditional entropy, of course, is going to be just the entropy of the topology-induced partition, which you don't know. You just don't know. All you know is that the conditional entropy is equal to that. So then the goal is to refine your data-induced partition to have your little robot go out and explore, create these maps with level sets, contours that are increasingly dense, but that as quickly as possible have this conditional entropy going to zero so that you're, in effect, discovering the topology. And the question is, can you do this? So, having said that question, The answer is, well, yes, you can do that, and that's kind of the subject of my talk. The key is to keep track of the Euler characteristic of the elements that you have in the data-induced partition. And the more negative the Euler characteristic is of a cell in this partition, the more likely it is to give you useful information about the topology. All right, so how does this work? Well, what I can do is, and the formulas get a little detailed, so I won't really say too much about them, except to give the idea of how they're used, is that we define this proxy for conditional entropy, which is h bar of a data-induced partition. And I note that there's this inequality, that h bar defined in this way in terms of the relative size of a cell and its Euler characteristic. This provides a bound, an upper bound, on this conditional entropy that I want to drive to 0. And then the result is that if I take an element in a cell that has Euler characteristic less than 0, then the update that I get by mapping a contour within that cell is always going to decrease strictly this proxy for conditional entropy. So if I can drive this proxy to 0, of course, then I drive the actual conditional entropy to 0. So what that says is that I look for the domain that has the most negative Euler characteristic, which is to say it has the most holes removed from its interior. And what I do is I try to map cells in that. And by doing that, I'm forcing the conditional entropy to decrease. All right, and here's just this said in another way with another cartoon. So that's how I'm going to construct my graph. And, oh, I should have plugged this in.
It's a simple game that will evaluate your ability to explore an unknown terrain. Exploring an unknown terrain is a task that humans seem to execute effortlessly. But this is the brain machine is really challenging. However, it's easy to make robots do simple tasks such as exploring a boundary. This is why this game will team up with a virtual robot and have been programmed to do simple motions. Your responsibility will be to make a pilot decision, such as where the coordinates and when you know enough to move to another area. The scenario is as follows. Due to an accident at a nuclear power plant, the area around it has been radioactively contaminated. An autonomous vehicle is sent to map the contaminated regions. This must be done as fast as possible so that the radiation spread can be predicted and evacuation procedures initiated. Your task is to give commands to the autonomous vehicle and tell it where and what to explore next. Here is how the game looks. The first thing you should notice is the clock, which shows you the remaining time that you have for exploration. The user interface has just one button to give you the ability to move to another area when you feel that you know enough. You explore the area by clicking in the free space, which makes the map a path between a radioactivity peak and a minimally contaminated region. Click one more time on the map path, and you get the constant radioactivity contour passing through this point. This is how your actors appear in 3 dimensions. You can click on the path as many times as you want, or click on the free space, which gives you another path between a maximum and minimum contamination point. Your objective is simple. Map the spread of radiation by mapping maximum, minimum, and the contours of constant contamination around it. Once you believe you know enough about the area, proceed to another one and start again. The area with either a low level of detail or with a high level of decide whether you have mapped the field with enough precision. You will be rewarded for your work.
Okay, so that's just an example of a game that we gave in the lab, and we had a bunch of engineering students who played the game, and what we're just interested in is how quickly they actually got reasonable representations of the topology of the domains that they were given. So I won't go into too much detail except to say there was a fairly wide range of responses, and we gave some exit interviews to the students, and some of the students said they just liked the idea of making the pictures as complete as possible, and they actually were pretty slow to discover what the topological characteristics were. Others were very minimalistic, and they very quickly discovered the underlying topology. And one of the things that was of interest is that the people who were very focused on discovering the topology didn't have a lot of variability in the time that they took with the game. They were very quick, and there was not a lot of difference from one to the other, whereas the ones that mapped a great deal of detail, they had a lot of variability. So let me just talk a little bit about one other possible application of this type of thinking about information content. Is suppose that you have a bunch of sensors, and now think about cameras that take images in certain ranges. And what you'd like to do is to know how to fuse images, all right? So this is not the problem of registration, all right? I assume that the registration problem has been solved, but suppose I take a picture of this room in a certain visual frequency range, and I take another picture in another visual frequency range. And I'm interested only in certain characteristics, okay? And what I'd like to do is to identify within these two images, where the characteristics of interest are, and to create a fused image. So one of the ways to solve this problem, which is the standard approach I think that most people who do imaging would take, is to do a multi-band image. So, and of course, if you're taking something like a color picture, and you've got 3 different bands that are going to create your colored image, so you've got RGB or whatever your choice of primaries is, then of course you do a multi-band image, and that's the easiest way to deal with it. But there are certain frequency ranges where it's not so natural to do that. And one of the ones that we just seized upon, because it seemed to be of interest, is if you take a visual band image and you take a thermal image, then it's not always so nice to do a multi-band that fuses them together, because thermal images overlaid on normal visual images don't look natural, all right? They can look just awful. So then what we'd like to do is to say, all right, if we have these different frequency bands and we'd like to keep the images separate, what I'd like to do is somehow put them together in such a way that in each band where the information is interesting, let's retain that and then make a composite image. So it's the same set of ideas that we have conditional entropies and so forth that we want to look at. We want to measure the information content in this same way that looks at the variability of the function and how that conveys information about the domain. And now what I want to do is step back, and instead of thinking about the conditional entropy of a field conditioned on another partition, the conditional entropy of a partition conditioned on another partition, I want to consider the information of a partition conditioned on a set. So now it's not the case that the entropy will always be less. The conditional entropy will always be less. And sort of, if I recall here, the definition of a condition of an entropy conditioned on another partition, then I have this inequality, which I mentioned a few slides back. But in fact, if I just condition the partition on a set, which is to say that I'm looking at the entropy within a restricted subset of the domain, then in fact the conditional entropy can be greater. And this is the thing that's going to make this sensor fusion idea work, is that what I'm going to do is I'm going to look for subsets of the domain that I started with, which maximize the conditional entropy if I restrict my attention to those subsets. And so then what I want to do is to get a set of possibly overlapping subdomains, okay, such that the information content of the ith sensor, where I ranges from 1 to capital N, is maximized on that particular subdomain. Okay, and I'm going to define a utility function here that is based on this quantity of related to the topology-induced partition of that particular sensor that I mentioned before as being a critical bounding element of the data-induced partitions. And then what I'm going to do with my domain is I'm going to create a decomposition into disjoint subsets such that the first subset, x sub 1, maximizes this information utility with respect to that metric that I just had on the previous slide. I take that out of the domain, and then I look at what's left, and I pick the subdomain of that domain that's left that maximizes the information utility on that subdomain. And in this way, I get a set of subdomains of decreasing utility such that they exhaust the entire domain that I started with, and such that if the index is less, then the information utility on that particular subdomain is higher. All right, and then what I do is I compare, for all the sensors, I form given that nested set of, or that hierarchical set of subdomains, I form a common refinement of those subsets. And based on that common refinement, every pixel in the image is assigned to a frequency range, such that the information utility of the set, the refined subset, is maximized. So here's an example where I took an image. This is a camera. There was no problem of fusion of registration here, because these cameras, this was the same camera with different frequency spectra. And here's in the visual spectrum a picture of a subject in my lab standing next to a dark room. And here is exactly the same image in the infrared spectrum. And what you see here that you don't see over here, of course, is that there's another subject that's standing in the dark room. So what I do is I form these partitions, these that are hierarchies of information content based on my information utility, okay? And then I form a common refinement, and I assign to each pixel in the entire domain, I assign that frequency spectrum where the information utility is maximized. And if I do that, I come up with this composite. So you see where the visual image looked good and where I could see a lot of useful information. That's what I get. And then in the part of the picture where the infrared image contained all the information, I get that over there. And so that's my composite image. So, okay, so I should wrap up. It's close to the end of the hour. This is a sort of a whirlwind tour of the kinds of things that we've been thinking about. But the idea of using information as a metric and as a performance goal for robots, I think, is an interesting one. And I think a number of people are starting to think about this in a number of different contexts. The same circle of ideas may be interesting in data compression of multiband images, and that's what I just finished with. And it's also the possibility that there's more to be learned about human decision-making styles using this circle of ideas, because in lots and lots of contexts, of course, the goal of human endeavor is to acquire information. And thinking about this in abstract, I think, is an interesting thing to be thinking about. And finally, there's some obvious extensions that one could try that we really haven't gotten into very much at all. But if you wanted to have, say, robotic reconnaissance of a domain where the field was varying in time, as it would be if there was some ongoing contamination, then you get into things like data rates and how quickly you're acquiring information versus how quickly that information is being generated by changing circumstances. So there's, I think it's a rich area for research, and I hope that some of my enthusiasm, at least, has come across to the audience. So with that, I'll conclude the talk, and I guess I'm certainly here for questions if people want to ask.
Thank you.